Hi everyone.
Hello.
Today we have Robert Booth talking to us about graphical symplectic algebra. Please, Robert, take it away.
Hi. Thanks for the quick introduction. Yeah, I'm going to be talking about graphical symplectic algebra. And I really didn't have much time to prepare for this talk, so my slides are a little bit scuffed. I've already noticed that at some point I recompiled and we lost the authors of the paper. Please bear with me. Hopefully it will go smoothly enough. Anyway, this is a presentation based on a paper that we just put out with my co-authors Tito Macaire and Cole Comfort. Sort of taking some of the results that each of us had obtained either in the setting of ZX calculus for odd prime dimensional systems or for sort of generalizations of graphical linear algebra, and putting them together in order to prove a completeness result for a category which we call affine Lagrangian relations, and I'm about to define in a second, which turns out to be surprisingly versatile in context to express a very wide variety of physical systems. Okay, so without wasting any more time, let's dive straight into the topic, starting with some very basic stuff, the definition of category relations. So I'm sure you all know at this point, but I'll go over it anyways. A relation from a set X to a set Y is defined to be a subset of the power set of X times Y. And what that means is that elements, can I not draw? No, I cannot draw this. Perfect. Means that the elements of this relation, this relation is a collection of elements of the form X paired with Y, where X belongs to the set X and Y belongs to the set Y. And you can sort of more conveniently draw these relations by picturing the set X as sort of a collection of points and the set Y as a different collection of points. And then whenever the pair points, say the top two points in these two sets belong to the relation, then you would draw an arrow or a line between them, and so you could picture an arbitrary relation as some arbitrary collection of arrows going from the set X to the set Y. Now, the nice thing with relations is that we can compose them. So if I have two relations from a set X to a set Y, and then from the set Y to the set Z, then I can compose these things. So I have two relations, something like this maybe, and like that. Then I can compose these two relations into, say, this relation is called R and this relation is called S. And then I can construct a new relation S composed with R simply by imposing that the new pairs of this composed relation are the pairs obtained if sort of I include a pair of an element in X and an element in Z, if and only if there's a path from that element to in X through R into Y and then through S into Z. And so I would get some number of new pairs in this new composed relation. In this case, I think just because of how I've drawn it, every pair in X and Z would be in the new composed relation. Now, the identities, there are also identities in this category for this composition, and they just take the form like this. This is the identity of the set X. And so there is a category whose objects are sets and whose morphisms are relations between those sets. Now, an important instance of these relations, which I'm sure you're all familiar with, is that if I have a function from the set Y to the set, sorry, from the set X to the set Y, then there's actually a relation associated to this function, which is going to be of this form here. And the nice thing here again is that the relational composition that we defined here, when you apply it to relations obtained from functions, is going to match exactly to the usual composition of functions that you would expect. Okay, so relations, finally, the last sort of bit of interesting structure, at least for us today, is that if you have two relations between arbitrary sets, then you can compose them in parallel simply by taking their product as sets. And this gives you a monoidal product. And so we have a monoidal category, and in fact, we have a symmetric monoidal category because there's a fairly straightforward to define symmetry. Now, relations are an interesting category of themselves, but in a lot of situations, there's more structure that you would like to take into account. And perhaps the sort of most common example of that is in the case where instead of considering sets, you instead consider vector spaces over a field, which are here called K. And then in that case, you can ask for your relations to not just be subsets, but to be subsets that verify some additional properties. And I'm sure you're not going to be very surprised that in this example, we impose that the relations between vector spaces should be subspaces of the direct sum of these two spaces rather than just arbitrary subsets of the Cartesian product, which matches the direct sum in the case of vector spaces. Now, there's two cases that I've picked out here. The first is the case of linear relations, which is where you just ask for a subspace. So in the case, for example, where I'm looking at relations from R to R, then I can picture that as a subspace or a subset of the plane. And the subspaces are essentially just going to be lines or the origin or just the whole plane. A slightly more involved, but not that much more complicated example is the case of affine subspaces. And in that case, you similarly take a subspace of your plane, but then you also shift it by some translation. So for example, this would be a subspace shifted by this sort of little translation X. And it turns out that if we take the same composition as what we defined in the previous slide for subsets, then you can straightforwardly check that this composition, if you take two linear subspaces or two affine subspaces and apply this composition, then as a result of that, you will obtain a linear or affine subspace of the sort of right type. And I'm not sure if there's a particularly nice geometric way of thinking about this. Pretty much you just write down the equation and check that you still have a subspace. But the sort of conclusion of this is that we also have a category now whose objects are K vector spaces or K linear spaces, and whose morphisms are linear or affine relations. So we're going to call these categories, linear relations over K or affine relations over K. And similarly to the case of functions and relations, if I have a linear map phi from X to Y, then the associated relation to phi is going to be a linear subspace. And if I have an affine map, that is a linear map plus a translation, then the corresponding relation is going to be an affine relation. Just as in the case of the relations, we also have a monoidal product and a compact structure, which also exists in relations, and I don't know why I forgot to put that on the previous slide. If you don't know what a compact structure is, it's not super important for the context of this talk, so I'm perfectly happy just to ignore it. Now, the categories of linear and affine relations are already quite interesting by themselves. There's a lot of systems that, in some sense, are described by sort of semantics, but with some kind of linear constraint to them. And in fact, there's a fair amount of work that's been done on the categories of linear relations and affine relations and subcategories of these to describe things like signal flow diagrams. There's been some work on doing describing electronic circuits internal to these categories. But what I'm going to talk to you about today, we actually need to introduce even more structure on the objects and the morphisms of our category. And I suppose it's in the title of the talk. What we're going to be working with are symplectic structures on vector spaces. So a symplectic vector space is just a normal vector space, only it's equipped with this thing called a symplectic form that verifies a handful of properties down here. I don't really expect you to read and pass these if you're not familiar with symplectic linear algebra. But really, I think the most relatable way of interpreting this, if you're familiar with quantum mechanics, is that these somehow relate to the commutation relations of, how do I do this? E to the I 2 pi omega A B over P. If you're working in p-dimensional quantum mechanics and you have the corresponding Pauli X and Z operators, then this somehow encodes the commutation relation. This is somehow the properties that you would need to encode the commutation relation between these operators at an algebraic level. If you impose that your vector spaces are equipped with such a symplectic form, then you can further ask that the linear maps between the vector spaces that you're interested in should further preserve this symplectic structure. So in this case, this looks something like this second line here, where I impose that if S is a linear map, then we call it a symplectomorphism if calculating the symplectic form in the image under S is the same as the symplectic form in the domain. And then we can play the same game as in the linear case, where we can have affine symplectomorphisms, which are not really saying much more than in the affine case. That is, an affine symplectomorphism is just a symplectomorphism plus a translation, which doesn't have to verify any further properties. Okay, so in the case of linear relations, we were interested in subspaces somehow respecting, or relations that somehow respect the linear structure of the vector spaces. In the case of symplectic algebra, we're now going to be interested in subspaces that also, in some sense, respect the symplectic form. And this is sort of another slightly tricky definition to put down. You can define this set S to the power omega, which is really just defined in the same way as you would define the orthogonal complement of a subspace or a subset. Only instead of using an inner product, you use the symplectic form instead. And then you can sort of pick out three different types of subspaces. A subspace is isotropic if it's included in its symplectic complement rather than its orthogonal complement. It's coisotropic if its symplectic complement is included in X, and it's Lagrangian if it's both isotropic and coisotropic. I once again can't really think of a good way to motivate this definition beyond this. it's a sort of fairly natural thing to look at when you consider examples from classical mechanics. You can see why this structure should arise. But on a geometric level, they're a bit tricky to picture because being Lagrangian, being a symplectic vector space implies that the dimension of the vector space is even dimensional. In dimension 2, the Lagrangian subspaces are just the lines that go through the origin, so not particularly interesting. And I can't picture two-dimensional subspaces of a four-dimensional subspace, which is what Lagrangian subspaces would be like. If you can, then I'm a bit jealous, but I can't give you a nice picture for this. I forgot to make this slide. There's a nice geometric interpretation of symplectomorphism. So the point is that if I once again look at the plane, so let's say I'm looking at R2.
Robert?
Yes.
Could I ask something about the last slide? Something that you read there.
Yes.
This commutation relation, did you mean actually just XA ZB equals that expression ZBXA?
Yes, possibly. Yes, that's right.
Yeah, I don't think this commutator thing works in finite dimensions.
No, you're right. Yeah. Ad-libbing a bit too much, but it should be ZBXA instead, or vice versa. I can't remember whether X or Z goes first on which side.
Probably a sign. I don't know. But yeah, that looks right.
Yeah, because obviously you can't represent that on a finite dimensional vector space. Sense.
Yeah.
Okay, yes, the geometric interpretation of these symplectic structures. The point is, if I have these two vectors x and y, then the symplectic form is essentially calculating a volume, or in this case, a surface of the parallelogram that you get by completing like this. And then the symplectomorphisms are sort of linear maps on the vector space that sort of can map this parallelogram around sort of any way you would like, but always preserving this surface area of the parallelogram. So you have things like you can shift this parallelogram up, which would be the translation part of affine symplectomorphisms. This would be, I guess, translation. You can do things like shear this. That is, you can sort of elongate it in one direction, so long as the volume always remains the same. You can rotate it around, and so on. So essentially, at least in the two-dimensional picture, the symplectomorphisms are the surface-preserving linear endomorphisms of the plane. And in general, they're going to be preserving some volume form in higher dimensions. Okay, so are there any further questions on what I've set up to this point? No? All right, perfect. Let's move on. So we're now ready to define this category of affine Lagrangian relations. So unsurprisingly, an affine Lagrangian relation from X to Y is going to be a Lagrangian subspace in the sense that I defined a couple of slides ago. And it's going to be an affine one. So it's just a translated Lagrangian subspace of the direct sum of X and Y. There's some sort of technicalities in how you define the symplectic structure on X plus Y that I don't want to go into, and they're not particularly interesting. So just take it for granted that this works more or less as you would expect. Then, once again, if you take two affine Lagrangian relations and you calculate their composition in exactly the same way as on the first slide of this talk, what you would get out the back of that is another affine Lagrangian relation. The identities, which are just the same ones inherited from linear relations, or even from relations, are once again affine Lagrangian relations. So we have a category that we're now going to call affine Lagrangian relations over a field K. And just as in every other example of relations, if I take an affine symplectomorphism, then the relation associated to that is actually going to be an affine Lagrangian relation. So we've somehow embedded this category of symplectomorphisms into this larger category of affine Lagrangian relations. This category inherits its monoidal product from linear relations. We can still use the direct sum, and it also inherits the compact structure from linear relations. Perfect. Now, the nice thing with affine Lagrangian relations that I sort of hinted at the beginning is that there are quite a lot of subject areas in which sort of naturally take semantics in the category of affine Lagrangian relation. This should be K, I suppose. So, for example, if we take the field K to be the real numbers, then you can see a lot of classical mechanics in at least the sort of linear part of classical mechanics lives in this category of affine Lagrangian relations. And you can see this in some of the work of Alan Weinstein and things that he cites. This is the other thing I forgot to say at the beginning. I realized just before this talk that I completely forgot to put in all the citations. So I'm going to have to remember off the top of my head who did what, and I'm probably going to get it wrong, so forgive me for that too. In using a different semantics, if you take K to be the field of, how does this work? The field of Laurent polynomials over a variable S, then you can interpret a large part of electrical circuits. And you can see this in some of John Baez's work. There's some stuff by Robin Coquette and his student. And I think some of one of the Zanazzi slash Filippo Bonchi papers has this kind of stuff in it as well. And then finally, there was a paper from a few years ago now by Cole, Comfort, and Alex Kissinger, which showed that if you take, maybe this notation is not the right one to make. If you take your field to be the finite field mod a odd prime P, then you actually get a category that's equivalent to the stabilizer fragment of quantum mechanics in dimension P, up to scalars. Okay, so I don't actually want to go any more into these examples because we're going to come back to them at the end of this talk, provided I have time, where we can actually draw some pictures in the diagrammatic calculus for some of these examples. Okay, so let's dive into diagrammatic languages, starting with spiders. And what I really want to say in this slide is that, as far as I'm concerned, at least in the context of this talk, I'm going to draw spiders like this, and like this, for some arbitrary number of input and output legs. And I always assume that my spiders are what Tiedemann calls flexometric, and what sort of maybe the community is more familiar with as the meta rule, only connectivity or only topology matters. And that is that I impose always rules such as this, which say that if I bend wires around arbitrarily, then this is equal to this, and so on. So it doesn't matter whether the legs of my spiders are inputs and outputs, it doesn't matter what order of the inputs and outputs is. I can sort of drag my spiders around arbitrarily around my diagrams, and it doesn't matter. The semantics are always going to be the same. Okay, so let's give our first fragment of our first diagrammatic language, which was defined Let me pull up the citation properly. Graphical, affine algebra, which is by Filippo Bonche, Robin Pilou, Paweł Słowacki, and Fadia Zanazzi. This is a slightly modified version of their axiomatization because they don't use spiders and they don't use flex symmetry, but it's completely equivalent. And so we can define a language GAA over field K, or graphical affine algebra, which is generated in the usual way for graphical languages by juxtaposition and sort of sequential composition by these three generators, where you have to be a bit careful that this last generator here is not flexometric, hence why we draw it with an arrow. Subject to the following rather large set of equations that you can't really simplify much more than this as far as we can tell. So I don't really want to dwell too long on this. Maybe we have a fusion rule, which is more or less what you would expect for the fusion rule for spiders coming from the ZX calculus. Here are labels for the white spiders are elements of the field, and they sort of control the affine or translation part of the semantics, and they add with the addition over the field. And then we have our arrow down here, which essentially is just doing a multiplication. We sometimes call a multiplier. That is, if I apply this arrow on translation by A, then I get a translation by A times B. And then we have rules for copying these things, rules for copying translations. And then if you're familiar with either maybe the ZH calculus or the odd prime dimensional stabilized ZX calculus, these rules will be familiar, which allow you to add multipliers and multiply multipliers together. Okay, so we can give a fairly, in this case, very cursory interpretation of these spiders as linear relation or affine relations. What we have here is essentially that the black or gray spider is sort of doing some kind of checking where if you feed it m copies of some element of the field, then it always outputs n copies of that same element. And then this white spider is a little bit trickier. It's imposing a relation on the inputs and the outputs, which is described by a set of linear relations, or here in this case, one linear equation, not relation, between the inputs and outputs. And sort of this affine part comes in here, and that it sort of shifts the outputs here by some constant A taken from the field, which is sort of describing this affine shift. In the case where you have a one-to-one spider, then it's literally just doing something like this, right? Or up the sign. And then the multipliers do sort of exactly what you would expect. If I give it an element B of the field, then it's going to output A times B, where I've now multiplied by A. Okay, so these set of axioms up here, it was proved in the paper that I just cited by Bonke et al. Are both sound and complete for the category of affine relations, or for this interpretation. And so what we get is that there's an equivalence of categories between this diagrammatic language and the category of affine relations. It's an equivalence of categories simply because I gave you the sort of non-strict version of the non-skeletal version of the category of affine relations. In the article, we do everything in the evil way, and so this is actually just described as an isomorphism. Perfect. Are there any questions about affine relations before I move on? No? Brilliant.
So maybe so you made the choice to make the what I would see as an X spider to make it flexsymmetric, and this is why you have this modified spider fusion
Yeah.
rule.
Yeah.
Where I'm guessing this single dot is like a minus sign.
So this single dot, I think, is somewhere, unless it's maybe derivable. But yes, this single dot here, pen back. This single dot here, I guess, is derivable, but we didn't put it, is the same as multiplying by -1.
Yeah.
If you look at the top right corner, this is a dot t dot 1.2. That's like saying that the square root of
Oh yeah,
is,
yeah.
with respect to it.
Yeah. Yeah. But then your multiplier thing is still has a direction to it, right? It's going from left to right.
Yeah.
But I guess if you also compose that with a single white dot, then the whole thing is symmetric again, as in self-transpose.
Why would it be? If you take A times this, why should that be self-transpose?
Oh no.
Yeah.
No, sorry. I'm trying to make the analogy to the qdit ZX, stabiliser ZX, where you can also define sort of symmetric multipliers by doing something with the Hadamars. I guess you don't have really have Hadamars.
Yes. So that's coming up in the next slide after this. Perfect. Okay. So if there's no more questions, I'll move on to what this talk is really about, which is this diagrammatic language, which we call graphical symplectic algebra, which is generated now by this sort of pair of two spiders that both have labels where A and B are both in the finite field. And we now have these boxes or Hadamard boxes or Hadamard, I don't really know what to call them anymore, which are once again flexsymmetric. Now, we made a decision in the axiomatization to use these boxes because they're flexsymmetric. What I mean by that is that now we have an equation like this that says that the wiring doesn't matter on these things. We could instead have used the multipliers from the previous, from graphical affine algebra, and added just a single unlabeled box as the generator. And we can then define labeled boxes as something like this. And these are once again flexsymmetric, which I think is what John was getting at in the previous discussion. And in fact, we don't even really need to have these as generators. We can just define this one using, I'm invariably going to get this wrong because I've changed this rule about 17 times while writing this article. I think this is right though. We can just use a sort of symplectic algebra variant of the Euler decomposition, which is the same essentially as the one which we used with Titouan and then with our follow-up article on the odd prime stabiliser fragment. So in fact, you can really just have the sort of same generators as graphical affine algebra, only add additional equations. But this presentation is flexsymmetric, which is nicer to work with. I think it gives a cleaner presentation. Okay, so now actually, and maybe surprisingly, the axioms that we need for the completeness of this category for affine Lagrangian relations are much fewer. Maybe that's not so surprising in that, just like in the case for the ZX calculus, we have this color change rule that allows you to change the color of spiders. And so you can sort of double up or halve the axioms because you know that any axiom you put in, you're going to get a inverted color variant of that axiom. And in a sense, that's what really makes the axiomatization of graphical affine algebra very big, is because you have sort of two copies of most of the axioms for each variant of the color. But yeah, this axiomatization is very close, I think, to the one we used with Baldassar and John and Leah for the stabiliser anti-twelve, with the stabiliser article we put out a few months ago, about a year ago maybe now. We have essentially the same fusion rule. Unsurprisingly, we have a bialgebra rule. I think the copy rule is essentially the same. Maybe the sort of more surprising rules are these rules times and plus. If you're familiar with the ZH calculus, then these are, I guess, quite natural things to see. And they're really just the generalization of these rules that we had up here for adding and multiplying multipliers, only now we sort of re-expressed them in terms of boxes instead, because I think boxes are, in general, nicer generators to work with. Now, the interpretation of graphical symplectic algebra, the sort of explicit one into fine Lagrangian relations, is actually pretty gross and I think very unintuitive to write down. The actual equations are big and don't tell you that much about it. So I'm going to cheat a little bit and give you an alternative interpretation, because we know that all affine Lagrangian relations are actually linear relations. Sort of, they have an underlying linear relation. This is the interpretation of our category into graphical affine algebra. And what you can see here is that essentially every generator gets copied into two color swapped copies of itself. And these essentially correspond to, if you think about this in quantum terms, you're basically tracking a bunch of X Paulis and a bunch of Z Paulis and how these evolve through your diagram. And then you have sort of a shift part on one of your gradings, a shift and a shearing operation that takes from one grading and sort of adds it into the other. If this doesn't really mean anything to you, I wouldn't worry too much about the details of this at this point. I think it's much clearer if you take the time to actually sit down, read it, and write it down and think about it for a bit. Yeah, this is the semantics of the category, and in particular, its sound for all of these equations. And it took far, far too long for me to come to a semantics that I was actually happy with and where the equations were as nice as I wanted them to be. Okay, so I'm running a bit slower than I really meant to be, but I'll try and do this anyways. Before we actually get into our proof of completeness, there's a little bit more syntax that I want to introduce. Now, what graphical affine or graphical linear algebra and graphical affine algebra, at the core of these things is really how you represent matrices and how you manipulate matrices. So the point is, if I have some matrix of elements over my field K, then this matrix can be represented inside of GAA in the following way. Firstly, you can note that these multiplier boxes are essentially just the equivalent of 1 times 1 matrices. And then this matrix K, I can represent in the following way. Hopefully I do this the right way and not the wrong way, where I'm looking, for example, here at a matrix that goes from 3 to 2. Hopefully I did that the right way around. Where if I have, say, an element here that goes from the first row into the second column, then this would correspond to a wire between the corresponding inputs and outputs of my overall diagram, labeled by with which sort of carrying the corresponding multiplier. And in this way, I get a sort of representation of my matrix internal to GAA. And really what this is saying is it's somehow doing exactly what you would do if you were to apply matrix multiplication to, if I were to feed maybe a vector into this thing. I sort of copy my my inputs, multiply them by the right elements of my matrix, and then add them back together on the output. You can also show that if I compose two of these things sequentially compose two of these things, these representations of matrices, then in fact this this overall diagram is equal under the equational theory, provably equal to the matrix that corresponds, the diagram that corresponds to the matrix you would obtain by multiplying those two matrices together. So you have sort of most of matrix algebra inside of GAA, but it's not particularly convenient to work with matrices in this way. If you get big matrices, then the diagrams are going to be very big and unwieldy to work with. So instead, we introduce a little bit of syntactic sugar, which is based on sort of a bunch of different things. There's some articles by Titouan on what he calls the scalable notation. There's some articles, some quite old articles by Robin Coquette, and maybe a more recent one by Fabio Zanazzi and his co-authors on how to draw diagrams for the strictification of a symmetric monodal category. I'm just going to treat it purely as syntactic sugar. So we introduce these generators where we have wires which are thought of thick wires that essentially just correspond to M here, in this case, M plus N wires that I've bundled together. And then I have these dividers and gatherers that just allow you to sort of split off M wires out of my collection of M plus N wires and inversely pack M and N, collections of M wires and collections of N wires into one bigger collection of N plus N wires. And then we can define matrix arrows, where now my matrices go from the type M to N, simply by taking this big diagram up here and then packing all of the input wires together. Oops. And all of the output wires together, and I get one big matrix arrow. And these sort of verify essentially the rules that you would expect. So like I said, if you have two in a row, then this is the same as if I multiplied the matrix and so on. And there are rules for copying these things, which are analogous to the multiply copy rules from graphical affine algebra. Okay, I'm running very slow. I don't know how, when people need to leave. But I'm just going to keep going and assume people will drop out when they have to go. Now, the real thing that I'm excited about, or at least one of the things that I'm excited about, is the following definition, which I'm going to give here quite informally, of scalable symplectic spiders. Now, the graphical language that I just gave you, the equation I just gave you, has has these spiders which are labeled by elements A, B of the field. And it turns out that we can pack graphs of these, or sort of bigger diagrams of these, into these scalable symplectic spiders, where now my spiders are labeled by a vector X and a symmetric matrix big X. And what these two things are doing is they're parametrizing, in the case of the vector, just some affine phases on these vertices here of the graph. And then the big matrix X is doing two things. The diagonal elements of X correspond to just sort of normal secondary labels of my vertices. And the off-diagonal elements parameterize a graph between the different vertices of this thing. And in general, here I've got sort of a scalable spider with 3 outputs, which means that I'm going to have 3 internal spiders in this diagram. Similarly, here I have 3 of these internal spiders, and then each of these internal spiders is going to have the same type, is going to take the same shape, let's say, as the scalable spider, but with types always just a single wire. So here I have, say, 3 internal spiders of type 3 to 2, and then a subgraph between them. Now, the reason that this is so much fun for me is that if you take an adjacency matrix G of a graph and you look at the 0G scalable spider, and you unfold this definition, so this is just the definition that I've given you informally from the previous slide. There's a formal inductive definition in the paper that I don't think is very informative. And then pull out, sort of unfuse all of these spiders, you'll see that this is really just the circuit for obtaining a graph state in the stabiliser fragment of the ZX calculus. And then in general, these symplectic graph-like diagrams, that is, diagrams corresponding to graphs but which have internal spiders that are not connected to any outputs, you can represent very compactly in this new calculus in the following form, where I just take some graph, essentially of the form up here, and then I say some m of these internal spiders are not outputs. Sorry, some m of the spiders in my graph are internal spiders, they're not connected to the output, and I just sort of block them off by composing with a co-unit, or just an m to 0 spider. Okay, are there any questions about this scalable axiomatization or this scalable representation?
Yeah, I have a question. So could you go back to the matrices that you presented earlier?
These ones, yeah. These?
No, earlier, like the matrix representation. I wonder, can I understand this matrix as a qubit version of modular matrix for a CNOT circuit? Because it looks like we can interpret every row as the input and every column as the output. And we can interpret the right-hand side, which is this bipartite graph, as a information propagation between the input and output after performing a qubit CNOT circuit, or this is not relevant.
So I'm not sure what you mean by modular matrix, but essentially what this thing is it's doing modular 2, I guess, is what you mean, is doing this map here. And this thing, if you're working over the field ZP, then this would be mod P. And so you would get exactly, I guess, what you're talking about. So this thing you could, if you want to rewrite it to some circuit of CNOTs, which I guess would look something like this. And you would get this sort of back and forth between this circuit of CNOTs and this representation as matrix multiplication. Right.
And why this graph is directed? Usually, wouldn't we use an undirected graph to represent the information propagation? Like, for example, matrix, is it symmetric?
Is it? These things here are not, like CNOTs are not undirected operations.
Oh, okay. So you distinguish between the control and target. So that's why you have this arrow here.
Exactly. So the difference, I guess, here between, in a sense, between these matrices here and the ones down here is that the ones down here are actually undirected, which is quite nice. They're doing something a little bit different than matrix multiplication, but yeah. Okay. Okay, if there's no further questions, I'll move on quickly to the axiomatization. So the nice thing, I don't really want to dwell on this super long because I mean it's cool and cute, but it maybe doesn't add that much, is that now these big scalable spiders actually verify a very simple set of rewrite rules that I think are very natural if you're familiar with both the graphical affine algebra and the ZX calculus. We have a generalization of the fusion rules, which is exactly the generalization that you would expect. We're now, instead of doing addition in the field, we're doing addition of vectors and addition of matrices, but everything works fine. We have this decomposition of matrix arrows, which I showed you from the previous slide. There's a rule that allows you to sort of cut these diagrams up into these sort of reduced, cut them up into smaller spiders with edges between the different spiders, which essentially just amounts to what's going on in this slide. And then we have this new rule, which we call thick color, but that maybe not the nicest name for it, which I think is the most interesting thing happening here. It's a generalization of the color rule from this slide here, where we had sort of the action of the Z linearly or by its inverse on A and by the square of the inverse on the second element of the label. We now have an application of the matrix Z and this sort of conjugation via the transpose by Z of the sort of matrix part of the label. And the cute thing here is that, in fact, using just this equation, well, using this equation and the fusion rules, you can actually derive the Euler decomposition of the Hadamard blocks. So I think this is a much sort of cuter axiomatization, and this seems a very natural thing to look at, whereas the Euler decomposition for me is maybe not so natural or not so obvious why it should be true. And this one's certainly much easier to work with in practice than the Euler decomposition. Okay.
And when you say Euler decomposition, you mean for the Hadamard, right? Not the generalized Euler for any qubit unitary.
Yeah. The Euler decomposition of the Hadamard blocks. Yeah.
One more question, because maybe I missed something, but I thought you said that all the stuff was syntactic sugar, but now you have a axiomatization of it. Like, what does that mean if it's syntactic sugar?
I realize I've been a bit ambiguous in how I presented it, but you can sort of add these gatherers and dividers as actual generators, take these sort of thick spiders as generators rather than the thin ones, and then impose all of these equations here, which is why we have equations here for the gatherers and dividers as well. I mean, this gives you another axiomatization, which is completely equivalent to the other one.
All right, and if you do that, then you get a multi-sorted prop, right? Where every wire is labeled by the dimension. And then exactly. Also, in principle, like for instance, this rule, these T-lex rules, they should also apply to like any possible set of numbers you could put on it that sort of matches.
Yeah, exactly.
Okay. Yeah.
Cool. Okay, so there's too much stuff going on in this article. Sort of one of the nicest results that we have from the paper, and which is a little bit hard to describe, is what I call symplectic elimination. And it's a way of eliminating, if I have this graph-like diagram here, where this part X corresponds to the labels of internal spiders, and Y corresponds to the labels of boundary spiders, or spiders that are connected to outputs. Then under the assumption that this matrix X is invertible, then I can actually remove all of those internal spiders and update the labels for the boundary spiders in the following way. I have this rule, which is essentially the Schur complement of this big matrix here on the left with respect to the top left X part. And I also sort of have this additional new symplectic, translation part that I get from doing this elimination. And this rule is actually a fairly broad generalization of both what we called in the article with John and Boldy and Leah and Titouan local complementation elimination, and pivoting elimination. That is, if you're careful about how you choose these matrices X, E, and the vectors X and Y, depending on the choice you make, you get a rule which is completely equivalent to local fragmentation elimination and a rule which is completely equivalent to pivoting elimination. Which is actually a bit of a surprise to me. I wasn't really expecting to come up with such a clean thing to replace both of these operations, which are somehow seem to be really important both for completeness and also for simplification algorithms in the normal quantum ZX calculus.
So this is very nice. I'm just wondering because like with ZX you can get rid of the internal spiders regardless of anything. You can always do it, but here you need this invertible property. Is this something that you need, or is it just that this is what you managed to prove?
Let me go to the next slide, which is about the normalization, and that will probably answer that question, which I'm going to do at a very high level without going into much of the details. So the point is, this is essentially the key part, the algorithm for turning a diagram into the normal form, which we call, based on previous names, the reduced AP form. If you take a diagram D and you assume that it's a state by turning all of the inputs into outputs using the compact structure, then there's a now at this point fairly standard algorithm for turning this into a graph-like diagram. So one which is of this form here, XX. Which is basically the same algorithm as was used in the original stabilizer completeness of Miriam-Backens, and then the completeness, both of the completeness results for the Q-dit stabilizer fragments. Then what you can do now is you can turn this using the rule from the previous slide into something of the following shape. You can eliminate all of the internal spiders, except that you have some that remain. How does this work? X, Y. You have some that remain, which are labeled by 0. You can't actually get rid of all of the internal spiders. There's always some that remain that are sort of unlabeled spiders that you're not really sure what to do with. Now, a slightly annoying thing with this step here is that I couldn't find a clean way using the rule from the previous slide to do it in one step. In general, for arbitrary fields, we're still using the same algorithm as for the qubit and qubit AP normal form completeness results. If you work in specific fields, say the real numbers, then things like the singular value decomposition give you an easy way to turn your matrix into the direct sum of an invertible one and the 0 matrix, and then you can just do this thing straight up. But in general, I couldn't find a way to avoid that. Does that answer your question, John?
Yeah, I think so.
Perfect. The next part of the normalization is to realize that, in fact, we're able to act now on this matrix E on the left or right, I guess, depending on how you're looking at it, by an arbitrary, maybe objective matrix A. And this means that we can do a Gaussian elimination of this matrix E. Oops, I changed colors. So you can turn it into something like this. 0, 1, E prime maybe, 1, E prime transpose, big matrix Y. I've still got this thing here. Where obviously this phases on this spider. And then finally, there's another set of lemmas that allow you to use the fact that you have this matrix 1, this identity matrix here, to act on the sort of top left and sort of left and top blocks of Y to replace them by 0 matrices instead. And so you end up in this form down here, where I've sort of replaced all of these submatrices of Y with zeros. I might have to have changed E, I can't remember to do this. And you can also do a similar thing with some part of the affine, with the translation of the first part of the label. And in fact, this is the normal form up to a permutation of the outputs. And this is like a very synthetic way of writing down the reduced AP form. It's quite straightforward how to interpret this as the sort of affine with phases quantum state, just by reading, because you can just read off the phases and the affine subspace from these matrices. Okay, so that's the completeness proof. I don't know if I have time to go into applications. I'm already over by 7 minutes.
I mean, I think if people want to leave, they're free to leave. So like, I think you can just keep talking if you want. Like we're not holding anyone hostage here, I think so.
You better not leave, or I'm never going to work with you. There. Yeah. So I mean, it's quite quick, because I've basically just given interpretations of various things into our language. So at the beginning of this talk, I said that we could interpret electronic circuits into affine Lagrangian relations. Now we can actually interpret electronic circuits into this category, graphical symplectic algebra, over the field. Just to remind, it's the field of Laurent series, Laurent polynomials over an indeterminate S, where an arbitrary junction of n plus n wires is just a gray spider with n inputs and n wires. A resistor corresponds to a sort of one-to-one white spider with this sort of leftover from flex symmetrization that you have to sort of keep track of. We can represent voltage sources, which are also sort of similar to resistors, except instead of this sort of symplectic shear part of the label, we're using the affine part to represent voltage sources. We can represent current sources as well. All of these things are actually interpretable if you take k to be just the real numbers. And then if you would like also, we can do inductances. Is that how you say that? Coils, I can't remember what they're called in English. Once again, using the affine part, but now we have this sort of Laurent, the inverse of this indeterminate appearing in our label. And similarly, capacitances are actually similar to voltage sources, but now with this indeterminate X. And via the completeness proof that we have, this says that we can rewrite any circuit. We can prove the equality of any two circuits written in terms of these components within our calculus graphical symplectic algebra. The sort of caveat is that not all diagrams in graphical symplectic algebra can be interpreted as electronic circuits, insofar as you can write down subdiagrams which don't correspond to any kind of electronic circuit. So things like simplification are perhaps not so straightforward. Okay, we also have an interpretation of stabilizer quantum mechanics in the case when the field is this finite field modulo an odd prime p. And this is exactly the same one as we gave in the previous two articles on completeness for stabilizer, odd prime stabilizers. We have a representation of the C0 or the CX, phase gate, the X, Pauli, and states and effects. maybe the only thing which is worth pointing out is that, and that might surprise some people, is that the Fourier transform interprets as the minus Hadamard box. And the reason for this is that you either have to make this decision, or graph states are all labeled by C0 or CZ gates that carry the inverse of the edge weight from the adjacency matrix of the graph. And so you have to make one decision. These two things are not compatible. And I thought this one was much less gross than the alternative. Cool. And then the thing that I'm perhaps most excited with about this is that you can begin to interpret a part of quantum optics into this. This is once again letting the field K be equal to the real numbers. And these generators here and here, these are taken from the PBS calculus, which is a calculus by Alexandre Clément, Simon Shane-Mansfield, Simon Perry, Shane-Mansfield, Nicolas Artel, for representing circuits, like linear optical quantum circuits. And we can actually interpret this into the calculus. The interesting thing, or maybe a slightly amusing thing, is that because in quantum optics, if you think of these wires as just a laser beam, every laser beam carries a vertical and a horizontal polarization, and each of these polarizations can carry an independent quantum state. And so the wires in the PBS calculus actually correspond to double wires in the affine Lagrangian picture. But yeah, we can interpret rotations of polarizations, beam splitters down here. I think this is a polarizing beam splitter, as well as phase gates, or something that they also call phase gates, which is not equivalent to phase gates from the stabilizer quantum mechanics case, but it's actually just a delay by a phase e to the I alpha. And yeah, that's pretty much everything I had to say, I think. There's some more stuff in the article that I didn't go into. We actually have an axiomatization of affine coisotropic relations via the discard construction. And we go much more in depth on some of these examples and giving examples of how you can do rewriting in a nicer way than had been done previously, for example, in the context of linear relations for things like electronic circuits. And then there's sort of lots and lots of follow-up questions that we're either working on or we would like to work on but don't have the time, such as trying to apply some of these ideas to quantum error correction, MBQC, extending the language further to be able to interpret much bigger fragments with quantum optics, and so on. But yeah, I think at this point I've already talked for far, far too long. And so I'll just leave it there and take any questions if there are any.
All right, thank you very much, Robert, for the great talk. Use the Zoom clap emoji or whatever you want to thank the speaker. We've already had plenty of questions throughout the talk, but are there any final questions people want to ask?
Yes, I have a question. So at the end, talk about its application in stabilizer quantum mechanics, and you have this P, and is this P a prime, or it can be a power of 2?
So it can be a power of 2, it can be 2. The problem, I think, at least for what I'm guessing you're getting at, is that if you take P to be 2 to the n, you get a perfectly valid category of affine Lagrangian relations over, say, Z2 to the n. But this thing is not equivalent to Zx, for like cubic Zx. I don't know what to call this. So it's easy to find rules that hold in the left side that can't be true for qubits and vice versa. And so there's some like subtle and annoying difference between affine Lagrangian relations when your field has characteristics 2 and the corresponding quantum sort of zx or